So the topic today is principles of payment evaluation. Before I move to principles of payment evaluation, let's talk about why we need to do payment evaluation. Okay. So if you think about a payment that has been constructed, once it has been constructed, it gets open to traffic, it gets open to climatic condition. And because of this traffic and climatic loading, there is a response that is generated by payment. Okay. And this response basically depends on what is the material property of the materials that have been used to construct this payment. Now, this response, or let's say periodic response, because we understand that the loading that we are talking about is because of vehicular loading. So usually a vehicle comes, loads the payment, then leaves, then next vehicle comes. So because of these periodic loadings that is coming, there is initiation and evolution of damage in payment structure. Okay. And it's the result of this accumulation of damage that you start seeing distresses happening in payment structure. Okay. This distress could be in form of cracks that you see, or it could be in form of permanent deformation that you see. Okay. Or if we talk about more about environmental influence, you may see moisture damage, or in fact rutting also as a result of traffic and severe climatic condition. Okay. So ultimately, we understand that a payment in its life will undergo distress as time passes. Okay. So if I would like to, as an engineer, start plotting deterioration with time by defining some form of a term for deterioration, I would, as I explained, will see that with time in x-axis, this deterioration will keep on increasing as time will pass. Okay. In the beginning of this time period, we understand that deterioration will be insignificant or will be zero, because that's the beginning of, or that was the beginning of or of the road for opening to traffic, right? So it is this time where the transportation agency or the government agency responsible for this road had invested capital for construction of this road. Okay. So you have this road constructed with investment from the transportation agency, which has now started to deteriorate. Okay. But then as this deterioration of this road is going to happen, um, there is no probably in further investment of capital from the transportation agency, but the road users who are using this road, especially the vehicle drivers or the owners of the vehicles, will experience increase in their fuel cost, right? And also increase in the maintenance cost of vehicle. So because of this, the transportation agency would like to have some threshold where at some point of deterioration, the agency would like to come, intervene, and do some sort of treatment to the payment, such that the deterioration level in the existing payment can be reduced. Okay, so you can see in this slide now that there was some initial construction caused by the transportation agency, and after that the road was open to traffic, deterioration started to kick in, deterioration went on till certain point, and then transportation agency decided to provide some sort of treatment which will involve, of course, treatment cost, so that to reduce the deterioration. Okay, deterioration level. And then again, after the treatment has been done, the road is open for traffic, and then again this cycle of deterioration will start. Okay, so this is a typical schematic of, if I can define some single unit for deterioration, how that deterioration will increase and then reduce, or will be reduced through over time. Okay. So therefore, from here we understand that payments need to be evaluated periodically. Okay, so payment needs to be evaluated periodically because we want to understand what would be our budget requirement. We want to understand what is the deterioration level. We want to understand at which point or of time we would like to intervene and provide treatment. Okay. So this evaluation is somewhat similar to health checkup that we do, or what we see when we go to see a doctor, right? So what happens when you go for a health checkup in a hospital? What does the doctor do? So the doctor looks for symptoms. So symptoms could be what is the skin color, what is the nail texture, right? Or if you have cold, cough. So all these symptoms are indicating what is your health condition or what is the deterioration level in any particular part of your body, right? If doctor wants, then he also specifies some test, and it could be a blood test or whatever. And in these tests, he's looking for certain parameters, right? So he takes these test parameters, and then these test parameters he relates to health condition or deterioration level in the body, right? So in similar way, we also, when we talk about payment evaluation, would like to look at symptoms that are there in the payment. Then we may like to conduct some tests to look at some parameters derived out of those tests to understand what is the health condition or deterioration level in the payment. Okay. So as we are talking about this health monitoring of payment, I would like to specify here that during this health monitoring or payment evaluation, we would like to look at two categories to understand the health of the payment. Okay. The first category could be looking at the structural adequacy of the payment. So what are you looking in structural adequacy of the payment? So when we are talking about structural adequacy, we are looking at, or we are concerned about, what is the load carrying capacity of the existing payment structure, or how will you look at the load carrying capacity of the existing payment structure? By looking at what is the surface deflection, what is the strain value, it will or it is going to generate at certain load levels, or what is the layer thickness in the existing payment, and or if you like some other material properties. Okay. So the typical parameter in this that we like to measure and monitor is basically modulus of the payment layer. So if you know what is the existing modulus or in situ modulus of the existing payment structure, then you can understand what is what is going to be its surface deflection, what is going to be its strain values. Okay. Another category in health monitoring or payment evaluation could be looking at the functional adequacy of the existing payment structure. Okay, so what is your concern when you are looking at functional adequacy of the payment structure? Your concern is basically to understand what is the comfort level that the existing payment is providing to the users. Okay. And also, in addition to that, you would like to understand how safe and economical it is to ride on this surface, payment surface. Okay. Whenever I'm saying surface, it means the payment surface. Okay. So what would be the typical parameter that you would like to monitor here or measure is basically what is the payment surface smoothness, or what is the riding quality that the existing payment is offering. So now if I talk about payment evaluation is a process to assess structural and functional condition of the payment, or let's say the existing payment, so that I can determine what will be the maintenance or strengthening jobs that will be needed. Okay. And also I can determine at which point or what point I would like to provide this maintenance or strengthening. So now, if you remember a couple of slides back, I was talking about deterioration versus time curve. So now I can, in fact, talk about structural inadequacy or structural damage in the payment structure with time. Okay. So if I talk about structural damage, it will increase with time, and then I can provide a threshold. So I can say that my structural damage in the payment structure should not go beyond certain threshold value. And if it is reaching at this particular threshold value, then I need to intervene and provide some treatment to the payment. In the same way, now my y-axis can become functional inadequacy or functional damage in the existing payment structure. And same way, the functional inadequacy is expected to increase with time. And at certain point, once it reaches some threshold value decided by the transportation agency, there will be intervention from the transportation agency to provide treatment which will take care of the functional inadequacy, right? Now, the treatment could be different for structural inadequacy and functional inadequacy, right? Depending on what is the damage, what is the inadequacy, the transportation agency can decide what type of treatment needs to be provided. So with this background, now we need to understand that payment evaluation can be conducted at different levels. Okay. So usually we talk about two levels of payment evaluation. We talk about payment evaluation at network level and payment evaluation at project level. Okay. So what do we understand when we say that I want to do payment evaluation at a network level? Okay. So when we talk about payment evaluation at network level, that means that the transportation agency is desiring to understand the overall network, what is the overall network health. Okay. So this means that when we talk about network level payment evaluation, we are talking about agency specific work. Okay. And we want to understand or evaluate the current condition of the payment network. Okay. So this network might have several projects in it. So I would, at the end of the network level payment evaluation, I would like to understand which projects, or I should be able to identify projects which are in need of maintenance and rehabilitation. And I should be able to prioritize these projects. Okay. And based on which I should be able to derive the budget requirement for my network. Whereas if we talk about project level payment evaluation, then we are talking about project specific evaluation. Okay. So that means that maybe I have a particular payment section for which I want to understand what is its existing condition. Okay. So, so in that case, I would like to understand in terms of its condition, what are the existing deterioration or failures, what are the causes of the failure that is there, what are the solutions or treatments may be required for the project. Okay. So that means when I'm talking about project level, I'm going more into detail and I'm conducting a more exhaustive payment evaluation, right? So in the project level payment evaluation, I would like to understand again what will be my rehabilitation strategy. Okay. So for all this, I might conduct several destructive as well as non-destructive testing, right? So project level may involve more number of testing compared to network level of payment evaluation, right? Because in project level, I'm going into more into details. Okay. So we understand a payment evaluation. So let's now try to put how a general evaluation procedure would look like. Okay. So if we talk about the general evaluation procedure, to understand the payment condition, the procedure might involve having several payment condition surveys. It might involve collecting data from field. In addition to that, it might also involve collecting material from field for assessing material properties. And based on this, deciding what is the payment condition, and in addition to that, if required, understanding what is the, or estimating what is the remaining service life. Okay. And based on this, deciding what will be the maintenance and rehabilitation measures and what will be its timings. Okay. So this is basically a general evaluation procedure. Now, to be more specific in payment evaluation, you might have several components or you might have several options. For example, if we are talking about functional evaluation, you might like to have visual inspection, you might like to have payment roughness measurement, you might like to have skid resistance measurement. Okay. And if we talk about structural evaluation, you might go for destructive testing, you might go for non-destructive testing. For destructive testing, you might directly take core samples from field and test it in lab, or also make observations by visually inspecting the cores. You can understand characteristic property of the material by measuring its modulus values and its strength. Whereas if we talk about non-destructive testing, in structural evaluation, in non-destructive testing, you might aim to obtain in situ material properties. Okay, so it's in situ because you're not taking out material to lab and test and obtain the material properties, but you're actually obtaining the material properties in the position the material is in the field. Okay, for example, if you want to measure modulus value of a certain layer in the payment structure, you might take material out from that layer and take it in lab and measure its modulus value, right? Or you might conduct a non-destructive testing, for example, falling weight deflectometer, and obtain its modulus value without taking any core out of the payment structure, right? So since you have not taken out sample from the payment structure and you are determining or estimating modulus value, the estimated modulus value will become in situ modulus value obtained from the non-destructive testing. Okay, so that's the benefit of conducting non-destructive testing. So non-destructive testing typically in payment evaluation could be static deflection method, in which you are not applying any dynamic loading or dynamic pulse load. Okay? Or it could be wave propagation, where you are measuring what is the velocity of the wave, or it could be impulse loading, where you are applying a pulse load to the payment. Okay, and you are measuring its response. Okay, so what you are doing in non-destructive testing, basically you are providing some external action to the payment, and you are measuring the reaction that is coming out from the payment. Okay, and based on the reaction that you are obtaining from the payment, or the response that you are observing from the payment, you are deciding or you are estimating the property or the condition of the payment. Okay, so we'll discuss more in detail as we move forward. So first, let's start with payment condition surveys, like what we were discussing in last couple of slides, that to do payment evaluation, you might do several payment condition surveys. Okay, so what is the goal of this payment condition survey? Okay, now in the payment condition survey, as I said, there may be multiple or many type of payment condition surveys. Let's talk specifically about surface distress evaluation. Okay, so when we are talking about surface distress evaluation, the goal is basically to look at or to provide payment condition rating based on what is the current distress level in the field. Okay, and based on this payment condition rating, the second goal is to select a maintenance strategy. Okay, so how this is happening? This is happening because in the payment condition survey, through visual, you're looking at the visual condition, or through visual condition survey, you are looking at the indicators of overall condition of the payment. Okay, and and not just visually, you might also have a quantitative understanding of what is the condition of the existing payment. Okay, so how will you perform this surface distress evaluation? So you might have several approaches. I am listing three uh, um, approaches. Basically, you can categorize it into three approaches. So first approach I have put as manual visual survey. Okay. So what is manual visual survey? Manual visual survey is basically um, you are walking over the entire length of the project. Okay. And as you are walking, you are measuring with measurement tape or any other tool that you have for physically measuring the distresses that are present on the project length. Okay, so that means you're manually actually measuring whatever are the distresses, and you are mapping this out in a form of a map, a form of a distress table or a distress chart. Okay, in addition to this, you might also note down what is the severity level of the distresses that you are seeing on the road. So this approach of surface distress evaluation is basically a manual approach. You might also adopt an automated visual survey technique. Okay, so most common automated visual survey techniques are basically based on image and video analysis, in which you collect video or images of the existing payment surface, and then you run it through an tool which will automatically analyze and give you what are the distresses and location of the distresses that are present in the project length. Okay, so this becomes my automated visual survey technique. Right? You might also have a semi-automated visual survey technique in which the data has been collected through automated method, could be image, could be video, but then this data is not automatically analyzed. In fact, the data is run in the lab, and then manually you analyze the data, deciding what are the distresses that are present in the project length. Okay, so since the entire process is not automated, this payment evaluation will become automated payment evaluation. Right, so I might have three approaches. I might have manual visual survey, I might have automated visual survey, and or I might have semi-automated visual survey. Right, this slide I have just put here just to connect with you guys on what we are talking about. So we are talking about distresses on the payment surface, which could be cracking, which could be potholes, which could be corrugations, which could be raveling, slippage, or rutting. There are many more distresses. I don't want to go into details of what are the distresses in flexible payment, distresses in rigid payment. Okay, so so we have understood that we can obtain these surface distresses through any of the approaches, but before analyzing this data further, or before deriving any distress index based on the observed or measured these field distresses, there are some issues that needs to be addressed. Okay, so what are these issues? These issues, as I told you, that the first issue is basically when you are looking at the distress, whether manually or semi-automated or automated, you need to understand the quantity of the distress, but in addition to that, you need to also understand what is the severity level of the distress. Okay, whether the distress is of high severity level, or it's a medium severity level, or it's a low severity level. I don't want to go into more details about severity level. That you can the definition of severity level based on distress to distress you can obtain from IRC code or ASTM standards. But just as an example, okay, when we are talking about, for example, fatigue cracking, okay, so when you see a single crack along the wheel path, it may be considered as a low severity fatigue cracking, right? When you have couple of cracks running along the wheel path, you may consider it as a medium severity cracking, right? When you have several cracks crisscrossing each other along the wheel path, then you might consider it as a high severity level fatigue cracking, right? So this way you will see that severity levels for different distresses has been defined in ISC code, so you can go through them to understand the severity levels, right? Then to form the data into a usable quantity, you would like to derive a rating scale, right? So this rating scale, as you are defining the scale, you can have the scale of any range, right? But commonly what you see is in practice, usually we consider this rating scale as from 0 to 100 or 0 to 10. Okay, so what is this rating scale? This rating scale is basically the scale over which you would like to represent the condition of the pavement, right? So usually if we are talking about 0 to 10 or 0 to 100 rating scale, the lower score is represented to be having higher distress, and as the score is increasing, the distress level is considered to be lower. Okay. Then if you remember, in the beginning of the presentation I had showed you distress versus time curve, right? And then I said that at certain threshold level, the transportation agency has to decide that it needs to intervene and provide some treatment, right? So for your distresses, or for the index that you will derive from your for your distress, you need to define this threshold value. Okay. Now, again, this threshold value you might define in terms of percentage or some number within the rating scale. So the typical number that is used is 60 if the rating scale is going from 0 to 100, right? So that means that if the distress index defined for the distress has reached a threshold value of 60, then that means that the transportation agency would like to intervene to provide some treatment, right? So to have this surface distress evaluation, these are the three important issues that you need to address before you can continue with your surface distress evaluation or analysis, right? So to understand about the pavement condition index that we follow in India, you can look at IRC 82 2015 on how to calculate payment condition index using the using distresses that are measured from field. Okay. Now you have obtained this field distresses. You have collected the raw data and you have also processed it to obtain distress indices, let's say, maybe in terms of payment condition index, PCI, or depending on which guideline you are using, whatever index you have calculated based on the raw data. But then this raw data has to be used finally to decide what treatment needs to be provided, or to understand at what time this treatment needs to be provided, right? So looking at the literature or the practices that are followed around the world, I have put it into 4 categories. Okay. So the first category I'm putting is the approach which is fully automatic distress collection and treatment selection. Okay. So you have collected the distresses from field, information about how much distress is there in the existing payment from the field in fully automated form, okay, using images and videos, and you have also analyzed it automatically, and the selection of treatment has also been made automatically. Okay. And all this has been done without considering what is the distress history. Okay. So what do you understand? So you understand fully automated distress collection. I have already explained you what this means in the previous slide. You also understand that based on this, you have to select some treatment, or the transportation agency has to select some treatment that needs to be provided to the payment. There is another point that I have made here is without considering distress history. Okay. So what do you understand by without considering distress history? So let's say I'm a transportation agency and I am collecting my payment distresses in my network in year 2021. Okay. And based on the distress that I have found in year 2021, I have decided what treatments should be provided to my payments. Okay. So that means that I am deciding what treatments to be provided based on a snapshot of information. Okay, I'm not looking at what was the payment condition in year 2019. I'm not looking at what was the payment condition in year 2017 or 2015. So in my payment evaluation, I'm looking at only a snapshot information to decide what is the current condition of the payment and what should be the treatment that needs to be provided. Okay. And this whole process is happening in an automated form. So now I guess you are able to understand the entire statement, that the distress evaluation is being conducted in a fully automatic distress collection and treatment selection form without considering the distress history. Okay. Now another approach could be collection of distresses manually and then treatment selection, again without considering distress history. Okay, so this is self-explanatory. Another option could be semi-automatic distress collection and treatment selection considering distress history. Okay, so what do you understand here by considering distress history? It means that you have collected the distress information in year 2021. You have also collected distress information for your payment in maybe some other year, 2019. You might have also collected distress information in year 2017 and so on. Okay. And now you're looking at what is the history of distresses in a particular payment, right? So what is the benefit of looking at the history of distress in payment evaluation? So the benefit is that uh, from the history of payment distress, you would be able to not just get what is the current distress, but also you would be able to understand at what rate the distress is evolving. Okay. So what is the benefit of understanding the rate of evolution of distress? So the benefit of understanding the rate of evolution of distress is that you can estimate at which or at what point the payment will reach its threshold value. Okay. So once I'm able to understand at what time payment will be able to reach its threshold value for distress that I have decided, I would be able to calculate what is the remaining life of the payment. Okay, that means the approaches in which the distress analysis and treatment selection is done considering the distress history usually will involve calculation of remaining service life. Okay, there is additional information when you're looking at distress history, which is basically evolution or how the distress or the rate at which the distress is is evolving over time. Okay. Now, the last category that I have put here is manual distress collection. And in addition to that, also to have digital images to verify the manual distress collection, and then selection of treatment type considering the distress history. Okay. So usually if you look at the transportation agencies around the world, they select one of these methods in their payment management system. Okay. So you understand hopefully now surface distress evaluation. Now I want to talk about evaluation of structural condition. Okay. So when I'm talking about evaluation of structural condition, I may talk about destructive approach, or I may have another approach which could be non-destructive, right? So let's start with our discussion with destructive test approach. Okay. So the usual practice in evaluating structural condition using destructive approach is to obtain sample from the field, right? It could be through coring, it could be through creating pits. So as you are collecting sample, uh, you are basically powering yourself to more details. So you might have more detailed data. Okay, you might take sample to lab, obtain mechanical property, physical property, chemical properties of the materials that has been used for the payment construction. Okay, you may understand what is the existing um, um, uh, properties that are there in the existing payment structure. Okay. Additional benefit of taking course from field is that you can inspect what is the payment layer thicknesses. Okay. And one of the major important um, point is that when you are taking sample from field, you are able to do an accurate characterization of the material. Okay. So for example, if we are talking about the asphalt mix, if I'm taking asphalt mix from the field, I would be able to do an accurate characterization of its viscoelastic properties. Okay. So these are the benefits of taking samples from field or conducting destructive test. But then there are several disadvantages also, okay, which makes this approach not lucrative. So what are these disadvantages? Major disadvantages are basically as it involves taking course or testing in lab. This is time intensive. So you require time, minimum 3 days. Let's say if you want to know the modulus of the material, so you'll have to take sample, you will have to probably dry the sample in lab, then you will have to condition the sample, you will have to test the sample. So minimum 3 days you require, right? Also, it is very resource intensive. For example, you can see in the picture, if you are taking core, you need to have a coring machine, you need to have power supply to coring machine, you need to have water supply, you need to have you need to have skill workforce. Another major problem is interruption to traffic. Okay, if you are taking cores, if you are taking field samples, you have to interrupt the traffic, you have to stop the lane and disrupt the traffic. Okay, also, because of all these reasons, you can only take limited number of samples, right? So if you have only limited number of samples, you cannot have a better understanding of spatial variability that might exist. Okay, or you may not be able to uh, ha- to understand or to identify homogeneous sections that might be there in your project. Okay, so because of all these issues, people prefer conducting non-destructive testing. So non-destructive testing is a valuable tool because through which you can understand the structural adequacy, and also because it is non-destructive test, you can also have a higher frequency of tests and understand spatial variability, and also understand uh, what are the homogeneous sections available in your project, right? So there are few popular non-destructive testings that we use in pavement evaluation. In India, we use popularly Benkelman beam test, which is one of the earliest and traditional non-destructive test technique that is used, right? There is a IRC code, IRC 81, that is that provides guidelines about how to perform Benkelman beam test and how to analyze the data. Okay. Although Benkelman beam test is an old test, there is lot of experience in the industry about Benkelman beam test. There is lot of data available, but then there is lot of limitations in conducting Benkelman beam test, and there's lot of limitations in the information that can be extracted from Benkelman beam test. Okay, I don't want to get into Benkelman beam test, but I would like to discuss about the limitations of Benkelman beam test so that we can move forward. Okay. So one of the major limitation of Benkelman beam test is that it's a static load test, and we understand that in pavements we deal with moving loads, right? So if you are sitting at certain point on pavement, you will notice that a load vehicles come and pass, then the next vehicle comes and pass. So the load that we are talking about is moving load. So the test basically doesn't simulate moving load, right? It's a static load test. Another limitation of Benkelman beam is that it is resource intensive, it's labor intensive. You require a truck with certain load. There is a requirement about tire pressure. Okay, so also you need people, you need a driver, you need a helper, you need a skilled person to perform the test. So it's resource and labor intensive. Also, since it involves a truck, it disrupts traffic, the lane has to be closed. Okay, and even after all these limitations related to the testing, there is limitation in terms of the information also that you can extract, because the test doesn't give you or does not predict properties of the layers, different layers that are present in the pavement structure, right? So it doesn't give you any characteristic property of the payment structure. So with all these limitations, now people are moving away from Benkel beam test. And if you'll see, there is a new test that has been introduced in IRC in 2014, which is basically falling weight deflectometer test. Okay, falling weight deflectometer test is also has been there for quite some time in industry. It's a non-destructive test in which you are able to obtain modulus value of different layers that are present in the existing payment structure. Okay, so with this, basically you are able to overcome limitations of Benkel beam test that I had explained you in the previous slide, because falling weight deflectometer, as I explained you, is a test which takes much smaller time, and it is much more labor and resource intensive. Okay, so you can also go through IRC 115 for more details, with the title, IRC title as Guideline for Structural Evaluation and Strengthening of Flexible Load Payments Using Falling Weight Deflectometer Technique. Okay. But I would like to discuss more into details about non-destructive tests for structural evaluation. So let's try to understand what is the principle behind this falling weight deflectometer. Okay. So to understand what is the principle behind falling weight deflectometer, let's look at a simply supported beam. Okay. So you can see here that there is a simply supported beam, and from our mechanics class, we know that if this simply supported beam of span L has been loaded in the center, or the mid of the span by load P, then the maximum deflection will be equal to PL cube divided by 48 EI. Okay, so this equation has been derived for this simply supported beam, right? So if you take this equation and plug the value of P, L, E, and I. So P you have you are applying as an external load, so you know how much load you are applying, and L and E and I you know from the geometry and material property, then you will always be able to find out what will be the maximum deflection in the beam, right? So since this equation is giving you what is the maximum deflection, it's a forward calculation. Okay, so let's term this equation as a forward calculation equation, which can give you the response of simply supported beam. I'm just giving you an example of simply supported beam. I'm not saying that this is the equation to measure deflection in pavements. Okay. Now, if you do some mathematical rearrangement and bring E on the left hand side, which is the modulus value, then in case you know the P value, L value, I value, okay, and if you have measured the maximum deflection for the simply supported beam, then by plugging the numbers, you should be able to calculate what is the modulus value, right? So this, in this way, you are basically back calculating the modulus value. Okay, back calculating how? Through measuring what is deflection in a simply supported beam, because you didn't know what is the E value of the material used in the manufacturing or construction of the beam. So you want to back calculate what is the E of the material that has been used to construct this beam. Okay, so this is basically back calculation, right? So the same or the similar principle is used in falling weight deflectometer analysis. Okay, so in falling weight deflectometer test, first to understand that to overcome the limitation of Benkel beam, we would like to simulate moving load in the test. So uh, so how to simulate the moving load in the test? Let's first understand what is moving load, what type of response does it create in a payment structure. Okay, So to understand what type of response is created in a payment structure under a moving load, let's assume that you are sitting on payment structure at point P, okay, and there is a vehicle which is approaching you at point P. I'm representing the vehicle by just its wheel. So this wheel initially is at point 1. With time, it is moving and reaching point 2, and then leaving the point P and moving to point 3, right? So what type of, if we talk about response in terms of surface deflection of the payment, what surface deflection you will notice at point P? You will see what I have plotted. You will see that the surface deflection at point P will be increasing as the wheel will be approaching point 2. It will be close to maximum, not maximum, but close to maximum when the wheel is right on point P, and then it will start to reduce as the wheel will start moving away from point P, right? So this basically is the deflection with time at point P. So since it's with respect to time, I'm getting deflection with time. I can call this as a deflection history, right? So it's a deflection history. So deflection at point P with time. Now, in falling weight deflectometer, I would like to create such a deflection history. Okay? So how can I create such a deflection history? I can create this deflection history if I can apply a pulse load, right? So I would like to apply a pulse load which will be of time duration similar to a moving load, right? And then because of this pulse load, I would like to measure what is surface deflection, right? So that's what is done in falling weight deflectometer. There is a test setup in which there is a loading plate which has a load cell. So the load is applied and through this loading plate and measured through load cell, right? As the load is being applied in a form of pulse, deflections on pavement surface is measured at several radial distances from the center of the loading plate. Okay, so you can see here in this slide there are sensors which are measuring surface deflections, and there is a loading plate. So the entire setup is towed by a vehicle, so the testing time is reduced and the traffic is not disrupted, right? In addition to load cell and geophones to measure surface deflection, there is also temperature gauge to measure what is the temperature of the pavement during the test. Okay. So as there is a pulse load that needs to be created through this loading plate, there has to be a pulse created, this which is created by dropping a mass on the plate. As the mass is dropped, there is a time from A to B, and B is the, in the plot you can see load extended on pavement versus time. So there is a time period between A and B. From A to B, the mass is traveling, and at point B, the mass has just started contact with the plate, right? So as the mass has created the contact with the plate, the load will increase, and as the mass has made the contact and then will start to rebound back, the load on the plate will start to reduce, right? So there will be a peak which will be reached, which is going to be point C, and as the mass will rebound back, the load will decrease and at some point will reach to 0, right, which is presented by point D in the plot, right? So you can see in the schematic there is a time period of pulse loading. In IRC 115 it is considered to be 20 to 30 milliseconds. If you look at older equipments, the time period used to be short, sometimes even 0.015 seconds. Okay, These days, if you look at equipments, usually you'll see that the time period is around 0.03 seconds, 0.035 seconds. Okay. So IRC 115 suggests that the target peak load should be 40 kilonewtons. Okay. If it is not 40 kilonewton, the data should be normalized to 40 kilonewton. So the test procedure will be as follows. You place the FWD machine at the point where you want to perform the test. You start with some seating loads, maybe 3 to 4 loads. During the seating load, you are not measuring what is the load and deflection. After the seating load, you start applying the actual test drops in which you will measure load and deflection. Right? You typically apply 4 load drops, but at least 3 load drops. Okay, and as you are applying these drops, you measure what is the load, that is stress that has been applied on the pavement surface, and what is the deflection which is measured on the pavement surface. In addition to this, you also measure what is the pavement temperature, and we understand that the pavement temperature at the surface will be different from pavement temperature at any depth in the pavement surface, in the pavement section, right? So what is suggested is that you measure the pavement temperature along the depth of the pavement. Okay? So usually you measure pavement temperature at 40 mm below the pavement surface. Okay. Once you have done these steps, you move to the next point and conduct or repeat the same steps to conduct the FWD testing. Okay. Once you have collected all the data at FWD data, you can use this FWD data where you know what is the loading, you know what is the surface deflection, to obtain what could be the estimate of modulus value for different layers in the pavement structure. Okay. So this is how a typical data will look like. The input is in form of pulse load. So the deflection will be in form of a deflection history. But in case you're assuming that the pavement structure is a multi-layer elastic structure, then you may not need the entire deflection history. You may need only the peak deflection values, right? So you will collect only the peak deflection values and then plot with radial distances. Okay, so if you'll plot surface deflections with sensor numbers or radial distance, you will see plots
Now,
somewhat similar. Hello.
yeah, now it's better. Now it's coming.
Okay. So you'll see a similar plot that I'm showing you in this schematic, right? Surface deflection versus sensor number. Okay. So this plot is called as deflection bowl because it almost looks like a bowl, right? Now, if you think by looking at the bowl, you may have some qualitative understanding if you consider two different pavement structures which have the similar or same pavement thicknesses, which has undergone the same loading but have different deflection bowls. Then from the deflection bowls, you may try to comment that which pavement structure is stronger and which pavement structure is weaker. But this type of comparison may not be a good approach for conducting pavement structural evaluation. Okay, so why it may not be a good approach? Because when you are conducting your pavement FW test on your pavement structure at two different points, the test temperatures might be different. Okay, for example, let's say at location A, if the pavement temperature was 20 degrees centigrade versus at location B, where the pavement was tested after 1 hour, and because of this time gap, the pavement temperature was 30 degrees centigrade, then we understand that if it's a flexible pavement, the pavement which is at 30 degrees centigrade will be softer. The asphalt mix will be softer compared to the pavement in which the asphalt layer was at 20 degrees centigrade. Okay. So if you want to analyze this FWD data, you need to apply some corrections so that you are analyzing all the data at some standard level, okay, or in some standard test for some standard datum analysis. Okay, so finally, in the analysis, let's say you have applied that temperature correction, and now you have temperature corrected deflection values, and you have also normalized with respect to loading value, so that now you have normalized deflection values. So now you have your data, raw data, in standard form for further analysis, right? So as I had explained you with the case of beam, in analysis of FWD data, you would like to understand what are the layer modulus values, okay, assume layer modulus value at which the pavement structure will produce calculated surface deflection same as the deflections that you have measured in field. Okay, if you are able to obtain through trial and error some assume layer moduli values for asphalt layers, which will give you pavement surface deflection which is matching the measured surface deflection, then those assume layer moduli value are nothing but the closest estimate of the existing in situ layer moduli of the pavement structure. Okay, so this process is nothing but called as back calculation process, right, for FWD analysis. Okay, so as I was telling you that you want to be close to the measured surface deflections through calculated surface deflections, um, we would like to define what is this closeness. Okay, so to define the closeness, you can define root mean square value, which can be defined as the difference between the measured and calculated surface deflections. Okay, so you can use the root mean square error. I have given you the equation here, where DCI is the calculated deflection at sensor number I, and DMI is measured deflection at sensor number I. So with this, and ND is the number of geophone sensors to measure surface deflection, right? So using this equation, you can calculate root mean square error, and you can use some optimization tool or some optimization technique to reduce this root mean square error to find that particular set of layer moduli which will give you minimum root mean square error, right? So in this process of analysis, we have indirectly defined our problem system, in which there are certain unknowns and certain knowns. So the unknowns are basically the modulus value of the layers that are there in the existing pavement structure, and the knowns are the values that have been measured or can be considered as known values. Okay, so the known values are typically considered as thickness, temperature, and Poisson's ratio. So this is a typical flowchart of back calculation process. I had already explained you that you have to start with some assumed moduli value for different layers that are existing in the pavement structure. Using this and layer thicknesses and load that has been measured in field, you will be able to calculate deflections using a forward algorithm. The calculated deflections will be compared with the measured deflection to obtain root mean square error or any other definition of error, which will be minimized through an optimization technique through which iteratively you will select new moduli value till the error has been minimized. Okay, and the candidate solution at which the error is minimized is the final in situ modulus values of the payment layer structures. Now, in all this process, the center line or the heart of it is the forward algorithm. The forward algorithm will decide what are the assumptions you are considering for the material properties that are there, right? In case you are considering all the materials that are there in the payment structure as linear elastic, then you will be doing a multi-layer elastic analysis, right? So the example is in the IRC 115, which is using KGP back, or there are other models in literature like mesh back, etc. Okay, if you are if you are considering the payment layers to be non-linear elastic or the asphalt layer to be linear elastic, then accordingly you'll have to choose your forward algorithm. Okay, so we understand now that through non-destructive testing you can obtain an estimate for characteristic properties. There are other non-destructive testing also, but I have picked these two because these two are the popular. These two are popular in India, and we have IRC code for them. Okay. Once you have done these tests and obtain through analysis the structural condition, then you can use this information in further payment evaluation. Okay, so what could be the application of this? It could be to understand what are the homogeneous sections that are there in the payment structure. Why do you need to understand what are homogeneous sections available? Because as I was telling you in the payment evaluation, one of the goal is basically to have ultimately selection of what treatments needs to be provided. Okay, now in case you have homogeneous sections decided based on payment structural evaluation, then you would be able to decide in which section what type of treatment need to be provided. Okay, so this way, through understanding the health of the payment section through homogeneous sections, you would be able to have a much more economical payment design. Okay, or much more economical uh, 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 selection of treatment for the existing payment structure. Okay. Another application could be in determination of remaining service life. So since you have now an estimate of what are the modulus values of in the existing payment structure, you can use those modulus values to obtain what is the fatigue and rutting life. Okay, and you can so you can understand what is the remaining service life using the fatigue and rutting equations that you have already seen, right, in IRC 37. Another approach is from MEPDG Asst 2002, in which it recognizes that the asphalt material is a viscoelastic material, and if you are dealing with a viscoelastic material, its modulus is not linear elastic. In fact, it should be defined in terms of either dynamic modulus or relaxation modulus, right? So in case you are recognizing the asphalt layer to be viscoelastic, uh, you will be defining your dynamic modulus with the x-axis as frequency, right? So you will have to have a dynamic modulus curve which will be varying with varying frequency. Okay. So using time temperature superpositioning, you can define a dynamic modulus master curve, which will be a characteristic property of your asphalt mix, right? So you might have the undamaged dynamic modulus master curve, which will be representing or which was obtained from or which was obtained during the construction or just after the construction when the payment was in undamaged form, right? So if you look at this curve can be mathematically represented using a sigmoid, So I'm showing you the equation of sigmoid. It has 4 parameters: alpha, delta, beta, gamma. So once the payment has been open to traffic, there will be some damage that will get induced in the payment structure. And when you will conduct falling weight deflectometer, or if you obtain the dynamic modulus through some non-destructive testing, the dynamic modulus value that you will obtain, or the modulus value that you are obtaining, is considered to be in situ damage modulus, right? Because the payment has undergone damage, right? So you would like to compare this damage modulus with the undamaged modulus curve, right? So if you compare, you can then you can then try to accommodate or move this undamaged master curve to obtain damage master curve by introducing damage factor dj, right? So this dj will be introduced in this sigmoid equation as a product with alpha. Okay, so you can see here alpha has been multiplied with dj, and now the dynamic modulus master curve is my master curve for damage case. Okay, so from here basically you can also obtain damage dynamic modulus master curve. So let me now start closing our discussion. So to close, we can, from our discussion, we can understand that we have shown that payment evaluation has several successful applications. Some of the application could be to determine what is the condition of payment, right? In terms of its surface distresses. It could be to understand or determine what will be the budget requirement for a payment network, or to decide what treatment type needs to be provided, or to understand or to determine what are the homogeneous sections in a particular payment project or payment section, or to determine what is the remaining service life. Okay, or you can also understand what is the damage that has happened in the payment layers as time has progressed. Okay, but while doing all this payment evaluation, you need to be careful about few points. So I have listed few of them. Few of the important points that you should consider while performing payment evaluation is that when you are doing a payment condition survey, you need to be cautious that you don't perform it during during rainy day. Okay, you should not perform payment condition survey at point where the payment temperature is too high, because at higher temperatures there is a tendency of the payment to close the cracks, right? So in case the payment is at a higher temperature, you may not be able to see cracks, or the cracks might have closed, right? Then it is advised that payment condition survey should be conducted always during a specific period of a year for better comparison with network condition history. Okay, so what this means is that a specific time period should be fixed. For example, all the surveys should be conducted, let's say, in the month of March. Okay, so there should be this time window from March 1 to March 38th, that all the payment condition survey should be conducted in this particular time period in all the years, so that the data can be compared. Okay. Then when you are doing payment surveys, you should understand that the accuracy and reliability of conducting automated survey is dependent on what is the quality of the image or videos that you are collecting. Okay, so in this basically you need to be careful about what is the pixel or the resolution that you are using, and also what is the speed at which you are collecting the data. Okay. Then when we are talking about structural evaluation, you need to be careful about what is the temperature, test temperature, and what is the standard temperature for the analysis, right? So this requires temperature correction. Then in your analysis, you should select material properties to be as close as possible to the field condition. And also, when you're performing non-destructive evaluation or non-destructive test, analysis of non-destructive test, you need to understand that your analysis is only accurate if you have accurate information about your cross-section, right? For example, if you are analyzing FWD data, your analysis will be only accurate as long as or to the extent of the accuracy of your cross section, right? And finally, if we talk about conducting FWD test or any other non-destructive test, it is advised that you conduct the test in the intermediate temperature range, okay? Because at higher temperatures, you may your assumptions about the material properties, for example, if you are assuming the material to be elastic or if you are assuming it to be viscoelastic, those may not hold, okay? So at higher temperatures, you may have the material not behaving as a elastic or viscoelastic material. So it's always better to conduct the test at intermediate temperatures. So with this, I would like to stop here.